Negative 3 squared. Positive 9. Yes, James, enlighten us, please. Okay, so my domain of my function is blocked to be only positive because, exactly, we have a square root and you cannot take the square root of a negative quantity. So it stops over here. Okay. Do we have any extrema? This is getting us into section 4.6. How would you go about determining if this function has any extrema? And if so, where? Where does it have any inflection points? If so, where? Are the extremas maximums or minimums? If so, where? How would you go about determining that? What's in your mathematical toolbox? Samit, enlighten us. And you look for critical numbers, zeros of the first derivative. Those give you possible what? Extrema, okay, because you're looking at the direction. Is there a direction change on the function? If you want to know if those extremas are positives or negatives, you must take then the second derivative, okay, and then you put those zeros of the first derivative into the second derivative, and if the second derivative is positive, what do you know about the function? If the second derivative is positive, the function is concave up. You gotta know this, okay? I know you're thinking about next semester already, but we're not through with this one, so please, 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 really pay attention to this chapter 4. It's concave up, okay? So I would expect to see a minimum somewhere in here. Where's that going to occur? Don't know. Okay, somewhere in here, though, it's going to occur. Could I use the inspire to get close to it? Yeah, but if I want the exact answer, I have to go back and use. Okay, use my calculus. Okay, so let's go on. With this function, I expect to see that as I take the inputs out farther and farther, that this thing drops off. Should we test it and see? Let's try it. All I have to do is tab. I'm trying to get over here. Let me see, that's why. Tab, there we go. Go up, and all we have to do is change the exponent on that denominator. I'm just going to backspace on that. And I'll put a 1 in there since it wants something in there. Do you agree with the answer we got? As we take this farther and farther and farther, getting more positive inputs, is the output going less and less and less? Going down? Yes. Okay. Take a look. Oh, by the way, how did we identify those? The numerator and denominator. We said that the numerator is greater than the denominator. And so as the input's going to infinity, what's happening to the outputs? There is no limit to them. Let's do this analytically before our analytical approach. What are we going to do? What will I multiply by? 1 divided by x to the 3/2, okay, and 1 divided by x to the 3/2. That gives me the limit as x approaches infinity of 5 divided by x to the 3/2 minus 2. This would be 3 divided by x to the 1/2 minus 4 divided by x to the 3/2. Once again, we're back to our Theorem 4.10. We get a 0 minus 2 divided by 0 minus 0. What do you know about dividing by 0? undefined, which means, again, that we're going to negative infinity. Okay. So if the numerator is greater than the denominator, is there a limit to the output values? What about this one? Let's do an intuitive. This is similar to asking the question, the limit, or looking at the limit as x goes to infinity of what? Numerator, what is insignificant as we take x larger and larger? The 5, so this is negative 2, x to the 3 halves, divided by 3x to the 3 halves. That's the same thing as the limit as x goes to infinity of negative 2/3. What's your answer? As the input gets larger and larger and larger, the output value goes to negative 2/3. Yeah. Now, what would this look like on the graph? As I take the inputs to be greater and greater and greater, the function is looking more like, or doing what?
A straight line, right?
Where? Horizontal line, where?
Negative 2/3.
Negative 2/3. Let's give it a try. All we have to do is go down here and let's just change that exponent in the denominator to be 3 halves. So now we're going to have a horizontal asymptote. Does it work? There it is. Okay? Negative 2/3. Analytically, how are we going to deal with this? Same way we've been doing it. Very good answer. When you get to the point of seeing things being so repetitious they become boring, you got it. You got it. You're seeing the big picture. You're seeing that each of these problems is not a new problem, but just another one with a different wrapping on it. 1 divided by x to the 3 halves, divide by 1 divided by x to the 3 halves. So I have the limit, x goes to infinity, 5 divided by x to the 3 halves minus 2 divided by 3 minus 4 divided by x to the 3 halves according to theorem 4.10. That's 0 minus 2 divided by 3 minus 0, or negative 2/3. So analytically, we get the same answer, and I would hope to. I would hope to have the same answer. Okay, let's go on, because not every problem's polynomials and similar polynomials. Let's look at this one. The limit as x approaches infinity. Now, do I really need to say the log base 10 here? No, I could just write log, because base 10 is so common. You know, we've got our numeration system, our decimal system, our monetary system, everything's a base 10, times 1 plus 10 to the negative x as 10 goes to infinity. Anyone want to jump in and rewrite this for us? I'll help you out. Limit, x goes to infinity, log of what? 1 plus, how about 1 divided by 10 to the x? Would that work? Okay. All I'm going to do is change the negative exponent to positive. As the inputs get larger and larger, what happens to 1 divided by 10 to the x? Now again, we're not doing a direct substitution, but we're kind of, if you think about it, we kind of are. So this is down to the log of 1 plus what? 0. As the inputs get larger and larger, what's the relative value of 1 divided by 10 to the x? Just 0. So what is the log base 10 of 1? Well, let's see. The log base 10 of 1 has some value. That means that, remember, logs are exponents. Exponents are always placed on what? A base. What's the base of our exponent? Same as the base of our log. So 10 to what power equals 1? And our answer is 0. Okay. Let's go on. Find the limit of x. If you need to, put parentheses around that. As the inputs go to infinity, what do these outputs approach? Now we haven't had anything with the limit of sine. Do you have your notes there? You do. Go back to chapter 2, our limit chapter. There was a theorem involving sine. What was that theorem? Okay, the limit as x approaches what? C. Okay. Keep searching. Erica?
The limit as x goes to 0 of sine x over x equals 1 over x.
Okay. So we got 2 of them. We have 2 of them. One of them is going to help us out. This is one of those algebraic moves that maybe we would think of. What if I let x be 1 divided by t? Just suppose. Okay, I'm just going to define that. And we're going to then find the limit as t goes to 0 of something. Okay? If I do that, then what does this become? Well, let's see. The limit as t approaches 0, x is how much? 1 divided by t times the sine of 1 divided by t. Well, let's see, that would be the limit as t goes to 0. This would be the sine of t divided by t. Now, how did I make this jump that if x is 1 divided by t, then we're looking at the limit as t goes to 0? Okay. As the input's going to infinity, okay, so t would have to be going to 0 in order for that to happen. Now can we see our way to, and that would be the second theorem that we have here? This would be equal to 1. Now, would you have thought about using this? No, probably not. Not unless you saw quite a few of them. This is not something we've been doing all the time, but this is a possibility. And a lot of times, the problems we see in lecture and you do for homework, we bring out, at least I try to choose things that you wouldn't normally think of doing yourself. There's lots of problems in there that follow the same thing we've been doing. But if you